to talk. Um, I really see teaching in general, education in general, but particularly the exams, as this two-way pact between students and instructors. All right, so as students, you need to trust the entire 140 instructional team to be committed to your education and to do the best job we possibly can to convey the information to you that we think is important, and particularly during these difficult times of remote education. And I think we've met that challenge, and I am really grateful to many of you who have reached out and expressed your appreciation to your GSIs who absolutely deserve it. They go the extra mile. They care very deeply about you. And several of you have made comments to Stet and I as well. And so we really appreciate that you recognize we're doing everything we can to be committed to your education in these challenging times. You also need to trust us, and me in particular, to give you a reasonable exam, one that is fair and fairly assesses what you have learned in this class. And I am fully committed to that as well. So in turn, we need to be able to trust students. We need to be able to trust students to act with academic honesty, integrity, and respect for others, and expect you to hold your peers to this standard as well. That is part of the honor code. And the good news is that faculty across campus, we all firmly believe that the vast majority of students at UC Berkeley do adhere to our honor code. And we sincerely hope that this is the case for 100% of the students in ARC 140. So I'm just going to start with that principle. So how are we going to try to reduce stress going into the exam? We're going to try to just make it really clear how we are going to be organizing this. So first, I want to talk about the timing of the exam. Some people have asked about that. The timing of the exam, unless you have heard from me individually because of a challenge with time zone or a DSP student, the exam will be as originally scheduled, which is a Monday, 7 to 10 p.m., the first Monday of exam week. We will get it out of the way. So that's really important to note. I then want to talk about our platform. I think an important part in what's considered best practice across campus is to use platforms that are as familiar as possible in terms of the tools that you've already used in this class. So that's exactly what we're going to do. We're going to start the exam promptly at 7 p.m. by logging into a Zoom link, and we will provide that on the syllabus and also through the announcements. And we'll start off gathering together just as we would in a physical classroom environment where we can answer any questions, review the process again, and get everybody started. Then the exam itself is going to be administered as a B courses quiz, just like we've been doing the in-class quizzes for the last last four quizzes have all been through B courses. Your homeworks have been through B courses. This is going to be a platform that is very familiar to you. Right? Now, the other thing that happens with in-person exams is if students don't understand a question, you want to be able to raise your hand and ask a question. And we want to absolutely make sure that we are giving you that same opportunity to ask private questions during the exam. We will likely be using Zoom as our platform for this. The exact details about that will be forthcoming, but please be assured for now that we will be allowing people to ask questions during the exam, just like you would with a paper-based or in-person exam. All right, go over some exam rules. These are also the same as the paper-based exams and how we're trying to mimic as much as possible how we've done this class in the past. So the exam is closed book. You're not allowed to reference notes, books, lecture slides, websites. You're not allowed to have any external devices, phones, tablets, additional computers nearby, just like you would in an in-person exam. So we are expecting and trusting all of you to follow those rules. The exam is also, as is the usual case, an independent assessment. This means you're not allowed to talk to your friends. You're not allowed to have assistance from anyone else while taking the exam. We also expect and trust you to adhere to those rules as well. Now, as we've mentioned before, all equations, conversions, material properties are provided to you. So that is already on B courses. It's called a useful information sheet. I've put it under files. I've put a link to it in the syllabus at the bottom of the syllabus where you see the exam noted. I've put it on the exam update page that I'll show you momentarily. I encourage all of you to print that. It is much better to have it on a piece of paper so you're not having to open up another browser window, which you're really not allowed to do during the exam. So take care of that before the exam, print it. On the exam logistics survey, several of you told me that you had trouble not having access to a printer. I have already mailed out that exam sheet to everybody who asked for one. So hopefully you have gotten it. If you asked for one and have not gotten it, please write to me. We've got now 2 weeks before the exam, so there's time, but I want you to write to me this week and let me know if you need one. Or if you think you had a printer and now you realize you don't, write to me with your address and I will physically mail you one. So in addition to having the equation page, also during the exam, you're going to want the sun angle calculator nearby. Right? So you either have those with you or we have posted those on the B Courses site so that you want to print any questions we'll have, we'll use the Berkeley latitude. All right, so you'll want to print the 36 or 38 degree latitude, depending on which version you have for Berkeley. What else do you want with you? So you want your calculator, you want pen and paper nearby for working out the equations before you enter the answers, just like you would for the homework. Encourage you to have water nearby, encourage you to have snacks nearby. Some people have found that chewing gum helps you stay alert and focused. I've heard that before, so feel free to have that nearby. And I know that everybody has very different living situations right now. It's a challenge for many of you that are sharing homes with a large number of people. I encourage you to discuss in advance with your housemates, whether you're with family or you're still in Berkeley with your peers, to make an agreement to set aside a quiet space, even if it's not your room or it's your room and you kick your roommate out, but have an agreement with your household to set aside a quiet space for people who are going to be taking exams. If you have challenges with Wi-Fi bandwidth, make sure that you also may have an agreement that during exam time, the rest of people, if they have, you lay off of non-essential activities on the exam. Now I see a question came in from Cam and I am going to address that, so hang on there, Cam. So those are the exam rules. Are there any questions about that? And then I'm about to get into more of the scope and format. So feel free to enter your questions on chat. And if I don't get to them by the end of what I want to talk to you about, I'll check that. Now, consistent with previous in-person paper exams, you have a 3-hour block to take the exam. It is not a 3-hour exam. It is not designed to be a race. We want you to be thoughtful. We want you to take time to breathe. We want you to take time to check your work. There will be plenty of time for that. So don't forget to breathe. Don't forget to relax, stretch, take little breaks if you need to. It's not a race. Right? The exam covers the entire semester, but similar to, in terms of format, similar to what we did, like remember your homework modules? We are going to break up the exam into short sections. So when you go on to B courses, each of them will be called a quiz. And I'm going to show you, before we break into the lecture, a practice exam I put in B courses, just so you can see the organization. It's going to be divided up based on type of question, phases of the class. And we're doing it that way because we think it'll mimic the idea of pages in a paper-based exam. It'll help you organize your thinking. Maybe you'll get through all of the true-false questions first, check all of your work, go through those carefully, and then submit it. Now, unlike the in-class quizzes, which were short, there were only 6 questions, we only showed you 1 question at a time, and you are not allowed to go backwards. We're not doing it that way on the exam. So Cam, that answered your question. So there's kind of a hybrid method though. So when you open up a quiz, remember the final exam refers to the whole thing, and each module is called a quiz on B courses. So maybe one of the quizzes says true, false, part 1, and maybe there's 10 questions on there. So take your time. You can go back and forth between those 10 questions, check your work, but then once you submit that module, that quiz, then you can't go backwards, all right? So that's the hybrid. We will show you more than 1 question at a time. You can go back and forth within one of those modules, but once you submit it, then you can't go backwards. So we want you to take your time within a module, check your work as much as you can before you submit. Now, on B courses, there are several paper-based exams. And when you're looking at those, I wanted to note a few things that are going to be a little different. But first, I'm going to check one more question. Somebody asks, is the final exam equation sheet the same as the one in the equation and conversions folder on B courses? I'm not going to open up that right now, but where you should go to be most certain, because there's a couple versions of equations, and I want you to be familiar with what you're going to use for the exam. You should go to the syllabus. You should go to the bottom of the syllabus where it says final exam, and there is a link to the equation page, which is exactly the format we've used in every other exam, and it's the file name is called 2020, so you make sure you have the right one. All right, so you're going to look at the paper-based exams, which are on B courses. There's a lot of examples there, and I wanted to make a couple of comments about changes we're going to make given the remote circumstances. First of all, if you look at the exam and there's clearly questions and you say, we didn't do lectures on that, then don't worry about it. We're not going to ask you. Sometimes in the last year of the class, we mix up the kinds of lectures we're going to give. There might be guests that we didn't have. So if you see something on acoustics, and we didn't do an acoustics lecture this semester, don't worry about it, all right? All questions, because we're doing it through B courses, all questions are going to be true, false, multiple choice, or calculations. There's no word answers such as fill in the blanks or short narrative answers. You'll see some of those on the sample exams. We're not doing that, right? Where possible, we're going to avoid or minimize the need for images. In our paper-based exams, we usually had a lot of pictures, and we know that from the quizzes, some students had trouble viewing those in B courses. So unless it's absolutely essential, we're just not going to have images because we don't want to create a problem there. Now, another thing that can be something you can do in paper-based exams where you're manually grading, because B courses is doing all automated grading, what we're going to do with calculations is we're going to break them into smaller components to facilitate that automated grading. So there's not going to be one big problem and then you get one thing wrong and you lose 10 points. We're not going to do that. We're going to break every calculation problem into small components. So if you make a small error, you only get a small number of points off. Along with that, we're going to avoid linked questions where your answer to part A is required as input for part B. That's also problematic in B course exams. So we're not going to do that. They're not going to be linked. You might have part A, and then for part B, and I'll show you an example of that, we'll say, all right, just assume the answer for part A was 100 and now move on. And that way we're going to give you the input, which may have nothing to do with what you actually got for part A, but it'll allow you to move forward so that the questions are not linked. And we think that's a really good way to give a fair exam. We're also going to be really clear in every time we ask a question about the units we're expecting for your answer. So that means that when you're working out the problem on paper, you want to check your units really carefully and, you know, cancel units when they show up in the numerator and denominator so you can make sure the answer you get has the units that we tell you we're looking for. We'll also be clear about the number of decimal points to include if you're carrying things forward so you're not marked down for rounding. So those kinds of things we're going to be very careful about. All right, let me look at the questions again. Maya asks, can you open each quiz on a new tab and leave the page open and submit all the quizzes at the end? No, you can only, no, I don't know if technically you can, but we don't want you to do that. And if there's a setting so you can't do that, we really want you to focus on one quiz or module at a time. You'll have plenty of time. Go back and forth, review your work, and then submit, right? So Preston asked the same thing. Do you have to submit a module before moving on to another part? That is certainly our intention. All right, one other thing. So we are limited by some of the mechanisms that B Courses gives us in terms of just settings, but we are also utilizing some of the mechanisms they offer that allows us to give students somewhat different versions of the exam. And so we want to even just reduce the temptation of some of you comparing answers with friends or with housemates. I know some of you live together, so just don't even try it, right? Because you're going to ask somebody what they got, they're going to give you a number, you're going to freak out, you're going to input that number, and it's completely different than what you were given. So don't even try comparing answers. So that's really important. Any other questions before I show you what we've put on B Courses? Type them in if you have them. All right, so what I want to do next is just share screen with you. All right, so are you all seeing the front page or the front page of B Courses now?
No, you're not sharing your screen, Gail.
Oh, thank you. Let me go back to that. Try that again. Oh, wait, hold on. It was off there. My blue button was off the screen. Okay, now are you seeing it?
Yes.
Okay, thank you, Dylan. So here's the front page of B Courses. At the very top, I added this morning, oh, look, final exam info can be found on this page. Here's the page. So this is new this morning. Everything I talked about today is here, right? So if you go, what did she say? What did she say? It's all here. If there are updates, we will add updates and we will date those updates so you can know if something new was added. Now, if you go to assignments, you'll see I put on this final exam practice. So what's important to note here is that it's very short because you already have under files, sample exams. These questions came from those. So it did not make any sense for me to just retype in an entire exam. So you go to the sample exams for content. The purpose of this final exam practice on the assignments is just for you to see structure. Again, to reduce stress so that you can see how it's going to be presented. So what you'll see here, for example, is I have practice, true, false, part 1 of 2, part 2 of 2. In this case, I've just put 2 questions. In the real exam, it might be 10 questions each, right? But I will be showing you right on the assignments how many questions, and that will enable you to get a sense of the whole exam. It will help you plan for your time. It will help avoid any surprises. So that's really important. So you can go through, each of these is what we called the module or the quiz. Now I'm going to open up this last one that says practice calculations. Okay. and I am going to show you, for example, how this is going to work. It may look very similar to your homework. The difference is if you see question 2, you'll see that I actually wrote to avoid linking parts to this question. For this part, start with a value of UA ref equals 800, which means question 1, you calculated UA ref, but instead of using that answer, we're giving you the number that you should use as input. And that way, we're not linking any of these parts. And if you make an error in one part, it's not going to follow through to the others. And that's also considered a best practice for using B courses for exams. And that's how we're going to do that. You can also see that I write answers in units of BTU per hour degree Fahrenheit, or answer in units of dollars. So we'll try to be very conscientious about how we do that as well. All right, so that's all I was planning to talk to people about. Does anybody have any other questions about the exam? All right, well, if you do, we also have an opportunity on Wednesday's lecture. We'll open it up if people have questions. You can ask your GSIs. You can use B Courses Piazza. I want to make sure that everybody understands how we're going to be doing this moving forward. So with that, I am going to start the lecture. So as I mentioned, if you saw my announcement, this is a keynote lecture that I've given at several places that I wanted to share with you. The intention today was to give our tour of the HVAC system in Worcester Hall, which I love, and I'm really sorry that we're not able to do that. However, we're doing this instead. Now, because I didn't think we were giving this, there's some parts of today's lecture that I actually incorporated into the earlier thermal comfort lecture, way back lecture number 2. So there'll be a tiny part of redundancy because I didn't think I was going to be giving this one. But that's just a little bit from the very beginning. So my talk today is organized into these first 3 parts, where I'm going to start with primarily a visual argument for why variability is important, and how this connects to biophilic design, which we've also talked a little bit about. Then I'm going to show you some research examples that talk about evidence for the positive and pleasurable responses to variability. And then I will conclude with some brief thoughts about how to apply concepts of experiential-based design and practice. And then I'm going to finish by telling you a little bit about a new project that I'm embarking on that I really haven't actually talked to too many people about. So I'm excited to be able to share that with you as well. So I've shown this before, but let's do it again. I want you to imagine for a moment, what would life be like if we ate the same foods at every meal, if we never experienced weather or changing light levels, if we listened to constant monotone sound, never had music or the songs of birds, and had no art in our lives to delight our visual senses? Well, I think we can all agree it would be pretty awful. But that's essentially what we're doing in our indoor environments when we design for static, uniform, neutral conditions in our buildings. And this is what I would call experiential monotony, and there's really nothing pleasurable about it. And the irony is that it actually is incredibly energy intensive to try to achieve this constancy. So we know that we all seek out places in the natural environment and in our recreational lives that provide experiences that are far from neutrality. So the question is, how can we create more subtle yet still pleasurable experiences in our day-to-day lives within the built environment? So I think the solutions need to start with a paradigm shift in how we even think about the environment. Our thermal comfort standards and our conventional building practice are all about reducing the negative. Right? The Western goal of conditioning seems to be if no one notices, if no one complains, then we're doing all right. But I think we need to create a new framework for this. And I think we can borrow from Maslow's hierarchy of needs, which suggests that we need to first satisfy our basic requirements at the bottom: breathing, food, water, before we move upward to aspire towards our higher desires for love and self-worth and creativity. So we can reinterpret this in terms of indoor environmental quality and sensory components of the indoor environment. In particular, I'll use the example of thermal conditions. At the lowest level, the goal here is simply to avoid heat and cold stress. And it's often the basis for occupational safety and health standards or guidelines for resilient buildings to be habitable in the event of power outages during natural disasters. Our buildings are generally operated at this level second from the bottom, where the goal is literally to just have neutrality, what I would call the absence of feeling. Some of you may be familiar with the ASHRAE thermal comfort standards. Actually, you should be familiar because we introduced them. Some of you may remember is probably a better way to say it. The ASHRAE thermal comfort standards, which are designed to prescribe conditions in which 80% of the people are going to find those conditions acceptable. That means that our standards are saying it's okay if 20% of the building occupants are unhappy. That alone, I think, is a pretty low aspiration. So what I'm suggesting is that we need to aim for a higher level of experiential delight in this third level from the bottom. And at the very top, I'm putting just this idea of well-being, a concept that's getting increasing recognition in the building industry regarding how we can create environments that support our physical, emotional health and our cognitive function and productivity. So how do we get beyond mere comfort and design for these higher level experiences? So what I'm going to propose, and the premise of my talk today, is that we need to move upward in that triangle by using sensory variability. That variability is one of the keys to moving upward. So what are the benefits of variable thermal conditions? Some of these are really well understood and documented. I just want to show you a few examples to kind of set the stage here. One, energy use. There's a tremendous energy cost to our practice of maintaining a very tight range of thermal conditions inside buildings. In the US, conventional buildings typically operate in a narrow deadband of about 2 degrees Celsius. So this graph is from work that was done at CBE, and it shows the annual energy savings associated with expanding the range of possible interior set points. And it shows it for 3 different climates. And what the results are telling us is that we can reduce annual HVAC energy consumption by around 7 to 15% by every degree Celsius expansion in either direction. And this is potentially enormous energy savings. So the question is, how do we widen the temperature deadband while still maintaining comfort? And the bottom of this graph is where we're suggesting some of those strategies by using passive or naturally ventilated buildings, what's also sometimes called free running buildings, providing increased air movement on the warm side by utilizing fans, utilizing energy efficient radiant systems. Stet talked about that a lot, that allow the building temperatures to float over a wider range, or personal comfort systems, which we showed you on the tour and I'll be talking about later as well. Now, there's also health benefits associated with variability. I think this is some of the most interesting work that's being done by Van Marken Lichtenbelt and his team, and they found that exposure to mildly cold or warm environments increases metabolism and energy expenditure, which can help to fight obesity. obesity. And they also found that for people with type 2 diabetes, exposure to mild and intermittent coldness increases glucose metabolism and increases insulin sensitivity by more than 40%. And this is huge, and it's comparable with the best medical treatments currently available for diabetes. So as a result, the authors of this study have advocated that buildings such as homes and offices where we spend a lot of time intentionally adopt drifting temperatures to create a more healthy environment. Now, there have been some limited but also really interesting studies on the effects of variability on our cognitive performance. This is just one example where they exposed subjects to both constant and sawtooth temperatures, as you see in the upper graph on the right. And the sawtooth temperatures had similar mean values as the constant. And they found, as shown on the bottom, that the variable temperatures reduced symptoms of drowsiness and difficulty in concentration. And the difference was slight, but it was statistically significant. So I think this is an area that needs a lot more research. We've talked before, we've mentioned that the costs of people in buildings is 2 orders of magnitude higher than energy operating costs. So if simply having floating variable conditions can improve productivity, then I think the building and business communities would find those results really compelling. And finally is simply the effect of variability on our perception, which is the focus today. So I want you to recall for a moment a familiar place in the built environment that makes you feel good. And I suspect when you think about those places, you would rarely describe them as experientially bland or neutral. They're more likely associated with some form of variability, maybe in the thermal senses, but maybe also in the quality of light or views or sounds. And many of these places also offer a strong connection to nature. And I think that's where we can learn a lot about our affinity for variability. We've brought up the term biophilia before in this class. This refers to humans' love of living things and our innate connection to nature. And the related term biophilic design is a way of designing the places that we live and work to try to incorporate the elements of nature that we most respond to. The theory behind biophilia is that it's actually a genetic product of our evolution outdoors, where variability was linked to our survival. We had to sense changes in weather to help us seek adequate shelter. We needed to be able to understand variation in color and form of plants to identify what was edible or toxic, quickly understand the nature of movement in our peripheral vision to know whether we should hunt or flee. So while I'm not going to spend a lot of time on this topic, for those of you who want to learn more, I think some of the best sources are the publications that have come out of the organization Terrapin Bright Green. And these, this cover from one of their documents shows one of the books that are available for free on their website, and they've done a really good job of documenting the scientific evidence of how biophilic design impacts our psychological, physiological, emotional, and cognitive health. And they talk about the various biometrics that people have used to assess that. And they also took the original work of pioneers in this field, Edward Wilson and Stephen Kellert, and they simplified their concepts into these 14 basic patterns of biophilic design that include multisensory connection to nature and water and so many other things. But in the context of this talk, I want to focus on patterns of variability of thermal and airflow in terms of finding some research examples to share with you. So before I show you some of the research studies, these are just a few examples of the benefits of thermal and airflow variability that are documented in the reports I just showed you. It includes the effects of varying thermal performance, thermal conditions on student performance, how light breezes can improve our concentration, and how changing air velocity can affect comfort and even short-term memory. So in the next part of my talk, I want to go a bit deeper into concepts of variability in terms of these three examples of research. So the first thing I want to talk about is this concept of alesthesia, which is the physiological basis for thermal delight. And an increasing number of people are starting to hear about this. It's got analogies to other senses as well. And the premise here is that rather than just kind of global feelings of I'm feeling warm, I'm feeling cool, the premise is that the hedonic sensations of pleasure actually come from a dynamic component of thermoreceptors in our skin, that our thermoreceptors have both a static and a dynamic component, and the dynamic component is what gives us the sense of pleasure. And as such, the best potential for alesthesia is going to come from having some degree of variability or contrast, either over time or over different parts of the body. So researchers often talk about this in terms of two types of alesthesia. The first is referred to as temporal alesthesia, which is the pleasure from thermal conditions that change over time that allow the body's heat balance to return to normal levels. So from a design perspective, this is often associated with transition spaces where you might move from a hot to a cold space. We've all experienced this. You're rushing to school on a hot day. You've been riding your bike. You arrive and your body tissue is just soaked with heat. And if you step into an over air-conditioned building, which I guess would not be Worcester, so imagine you've ridden your bike to the store or a movie theater, and if you go into this over air-conditioned building lobby, it helps purge that heat. And initially, it's going to be very pleasant, right? You get that feeling of relief. But if you stay in those same conditions, it's going to start feeling cold over time. So the point I want to make here is that in general, temporal alesthesia is more likely going to occur when the body is in a less comfortable state to begin with. So remember that because we'll come back to it. The second type is spatial alesthesia. And here, when I talk about spatial alesthesia, I'm not talking about physical space, I'm talking about your body. Spatial differences in temperature or heat flux across the skin surface. So this type tends to occur when these differences are localized on the body, when we're feeling a whole body warmth and there's a distinct pleasure from a breeze on our face or putting your hands on a cool surface. Or overall, if we're cold and we feel the radiant heat from the fire on the front of our body, it doesn't even matter if the backs of our body are cold. So a lot of these familiar examples are in our recreational lives, but from a design perspective, this has a lot of implications for what we like to call people-based rather than space-based conditioning. How are we making our bodies comfortable, not really worrying about the whole volume of space? And another interesting point about this is that in general, we do not necessarily need to be feeling uncomfortable for these sensations to occur. So the primary goal for spatial alesthesial pleasure is to be able to have these sensations for longer periods of time. Now, this graph shows some early and often cited studies by Maurer, which helps illustrate this basic concept. So the body was initially in either a neutral or cold or warm state. Those are the three lines here. And then the hand was exposed to different temperatures, which is what's shown on the x-axis. And the y-axis is their subjective feelings of pleasant or unpleasant sensations. And what's interesting is that the only way to get to the more pleasant sensations above neutral is if you started with a slightly warm or cold body and then experience some contrasting conditions that were in the opposite direction. And if you look at this green line where you start off feeling neutral, the best you can do is just stay neutral or slightly comfortable. So the design challenge here is that we need to understand the realistic boundaries of what is actually what is actually realistic to achieve in the indoor environment. So that's what's represented conceptually in the purple rectangle here. So we're not talking about purposely creating extreme uncomfortable situations, but how can we create more subtle opportunities for creating thermal pleasure, right? So some analogies might be, how hungry should we be to enhance the delicious taste of food? Or how long should our sweethearts be away to enhance the feeling of seeing him or her? So as a framework for studying these questions, the red and blue zones at the top of this figure represent one's initial thermal state and therefore the potential for alesthesia. And it's rooted in this very complex relationship as shown in the lower images, starting between the environmental conditions that affect our thermoregulatory systems. And then we've got this neurophysiological relationship between the dynamic activity of the skin's thermoreceptors and our psychological response, or ultimately our feelings of pleasure. So in the middle, these light red and blue zones that are called acceptably warm and cool. These are the zones that are best suited for design implications in the indoor environment, where spatial alesthesia provides opportunities for sustained thermal pleasure. And in the more extreme outer zones, that's where the body starts to feel unacceptably warm or cold. And physiological control mechanisms might kick in, such as sweating or shivering. And even though there's a strong potential for feelings of pleasure here, there are fewer design opportunities because ideally we really don't want building occupants to get to that more extreme point to begin with. But there may be some potential for thinking about transition spaces for short-term temporal pleasure. So the new image I've just replaced on the bottom is a conceptual representation of research experiments that Tom Parkinson did. And Tom did this as part of his PhD with my colleague Richard Dedere at University of Sydney. And Tom now works with us at CBE. He's a wonderful colleague. And what he did is he created this sequence of exposures that would precondition subjects in progressively warm and cool conditions, and then would expose them to either step changes or ramps using combinations of temperature changes, fans, heating elements that were explicitly modeled to represent potential real-world circumstances. So his work was pretty extensive. I'm just going to be showing you one summary graph that combines the results from many of these experiments. So the conceptual diagram of this experiment is shrunk down on the bottom. On the figure on top, it's now showing people's votes on the thermal pleasure scale on the y-axis. And it's showing them both 1 minute prior to the transitions, represented by the gray diamond, and then immediately following the transition, which is the green square. So there's two patterns that are evident. In all except the two middle experiments, A1 and B1, which were the only ones where subjects actually started at a neutral reference. For all of the others, the direction of change was always upward to a more pleasurable response. And that confirms the theories of alesthesia. And the second thing to notice is that with the exception of B3, where there was an anomaly, both the intensity of the post-transition vote, the height of the green square, and the magnitude of the change, the length of the arrows, increased as the initial states moved from the moderate to the more extreme. And what happened in B3 is it just turned out that there were some residual effects from the heating in B2 where people were still feeling warm fuzzy, and so their initial vote, you could see, had been raised because of those residual effects. So there should have been a longer period of time before those experiments. So the second area I'd like to talk about, well, first, are there any, let me go back and check the chat. If you have questions, go ahead and put them in there, and then I'll come back and check, or Sierra can give me a holler because I'm not always paying attention to it. Right, so the second area of research that I want to talk about is variable air movement. Now, we've shown this building before, the Bullitt Center in Seattle. It's the largest building to have received the Stringent Living Building Challenge certification. And the air movement in this building comes from a combination of the ceiling fans and the operable windows. All right, so how does air movement affect us? There's two physiological factors that influence the effect of air movement on comfort. The first one is the relationship between air movement and convective heat loss from our bodies, which we've talked about before. So in this case, what happens is if you increase air movement, you're increasing the rate of convective heat loss from our skin. This is well known. I'm not going to talk about it much further, except the main point I want to say now is that the way we describe this relationship is merely this relatively simple metric of mean airspeed. And when you did your homeworks and you used the thermal comfort tool, you were able to input airspeed and find out how it compensated for warmer temperatures. So you did that in your homework. That's how the tool works. But the second factor I wanted to talk about is actually much more complicated. And it's about this sort of more nuanced ways that air movement can influence the flux of skin temperatures and the different activity of our cold and warm thermoreceptors. And then ultimately, how that activity then affects our subjective perception of thermal sensation and pleasure. So it turns out that it's not just mean airspeed, but it's actually this more dynamic quality of variable patterns of air movement that play a big role in the dynamic component of our thermoreceptors. So here's an example of different metrics that researchers use to describe the complexity of air movement patterns. And the most important point I want to make here is that if you look at this list on the left, each of those actually behave very differently if you're looking at air movement patterns found in nature versus those that are found by just conventional mechanical fans. So whether you're looking at the velocity distribution, something called turbulence intensity, which has to do with the variability, power spectrum, which is another measure of variability that has to do with the rate of change. All of these, it turns out, makes a big difference in what those patterns look like in natural wind or what they look like in fans, and how it actually affects our thermoreceptors and ultimately our sense of pleasure. So let's look at this last item on the list, the pattern of variability. This is some early classic work by Tanabe in Japan, who exposed subjects both to constant and sinusoidal patterns of air movement that had the same mean air velocity. So the patterns, the graphs on the right just show you what those patterns look like. And what they found is that subjects felt cooler with fluctuating air movement, even when the mean was the same as the constant. So what does that mean? That means that you can actually achieve the same comfort with lower settings of the fan if it's fluctuating instead of just being constant. And what that means is you could potentially run the fan at lower mean velocities. You can use less energy. You can have less disturbance from papers blowing. Now, 10 years later, this is another study done at Tsinghua University where they also tested fans with these different airflow patterns. And they found that people had a much stronger preference for patterns that were simulated to reflect the fluctuations of natural wind. And the least favorite were actually these constant patterns. So they actually designed these fans where the frequency would change and it would model well-known places in the natural environment, whether it was the beach or the mountains. So the last topic I want to talk about, last research topic I want to talk about, is this idea of moving away from centralized thermostat-based controls and considering person-based conditioning systems where people have individual control so they can match their personal preferences at any given moment. Now, way back in the beginning of the semester, we did a tour of the labs and we showed you our chairs. So you've seen this. We're doing a lot of research on personal comfort systems. We showed you that we had foot warmers, that we had personal fans. These chairs use very low energy. So it's 14 watts for heating, 3.5 watts for cooling. If you go and get one of those little floor heaters from Ace Hardware that you plug in under your desk, those are more on the order of 1,000 to 1,500 watts for heating, just to give you a sense of the difference here. They've got user controls for cooling and heating. Some of you sat in those. They have separate controls for both the seat and the bottom. It allows you to save energy by allowing wider HVAC temperature set points. Remember one of the first graphs I showed with the curves that were going upward? So if we can increase, widen the ambient set points and then of the air overall, and then find ways to condition bodies rather than space, there's enormous potential for saving energy. Now, these versions, research versions, you're able to have Wi-Fi and Bluetooth communication with the BMS system so that we can collect data. And we made a lot of these for research, but we've got them out in the field and in the lab. So just to give you a few examples of some of the research findings from this study, we looked at the chairs along with fans and foot warmers, food warmers, note to self, fix that. I just noticed that. It says food warmers. Hold on, making a note for myself. That's pretty funny. No, you cannot warm your, well, I guess you could put food in those little foot warmers, but you shouldn't. All right, so what did we do? We got these chairs in the field. We put them in the lab. We used them by themselves. We used them in combination. And we found that over a 20-degree temperature range, we got more than 90% of the people feeling comfortable. That is just outstanding. And then in the field, we were able to up that to 96% thermal acceptability. And people were using the chairs almost 3/4 of the time when they were seated. Now, another cool thing when you use these in research setting where you're collecting all of this information, we were able to collect a lot of information about the individual usage patterns. So I'm going to show you two graphs. This one is shown just for a single person. And this is showing is how one person, just as an example, their thermal preferences for heating shown in red or cooling shown in blue vary significantly throughout the day. So they might want heating in the morning, they might want cooling in the afternoon. And we can also look at all of the results for multiple people. So this is an example that shows the inter-individual thermal preferences, that they vary widely, even when people were exposed to the same ambient conditions. So I think this graph is really important for emphasizing that we need to give people personal control so that one person can create the variable conditions they want and change them throughout the day, and you and your neighbor may want completely different things, and that you can also get it. All right, so what I now want to talk about, I think that no matter how much research we do on these topics, and I love my research group, I love all the research we're doing, but we're doing applied research. We're trying to make a real difference in buildings, and we're not going to do that unless researchers do a better job communicating their results to designers. And one of the things I really appreciate about the CBE partnership, we've got 50 industry partners, is they keep us on track with that. They are constantly inspiring and motivating and checking with us that we are communicating our research in a way that is going to be useful to them. So they help us identify problems that they are having, challenges that can be addressed by research, and they also help us communicate that research in ways that are going to help impact their decisions about manufacturing, about design, about operation of buildings. But far too often, we've got designers thinking on the left and researchers thinking on the right, and the researchers are thinking about what are our bodies experiencing, and they're doing tests in the lab that are completely just in the mindset of researchers and not really thinking about the practical implications of a picture such as on the left of how do we design and operate physical environments that might be creating those conditions. So we need to get those worlds talking to each other. And one of the ways we can do that, I think, is be thinking about this connection between what our bodies are experiencing and what's happening in the physical environment in terms of both spatial and temporal patterns. So I'm going to offer a framework that I've been playing with a bit to try to organize design patterns into a matrix where the columns here might relate to the ideas that I talked about previously as spatial and temporal alesthesia, about how our bodies experience these different conditions, where the rows might relate to the design and operation of buildings, the building space and how the building space, how it changes over different zones in the building, the uniformity, or how it changes over time. So let's just give examples of these. Let's start in the top row, which are examples of ways to describe spatial characteristics of physical space that are non-uniform. Okay? In the top left, these are examples of spatial non-uniformity that may produce a whole body experience as the person actually moves between spaces. So examples might be the differences in air temperature between the interior and perimeter zones of a building, or perhaps separate rooms in a building that have different thermal properties that people move through. In the top right, these are ways a person experiences these non-uniformities over different parts of their body. So the person might be standing or sitting still, and different parts of their body experience these asymmetric environments. Maybe it's a radiant asymmetry, either intentionally created by a radiant system with a warm floor, cool ceiling, or maybe you're standing in a room with single pane cold windows. In other examples, maybe the room air is vertically stratified. Maybe you have the heated and cool chair that I referred to. So for any of these, if these are pleasurable, these can be considered examples of spatial alesthesia. Now let's look at the bottom row. These are examples where the environmental conditions in the physical space change over time, what we would typically call non-steady state or dynamic or transient conditions. Bottom left, again, are whole body experiences. This is what we study a lot in labs when we do lab studies of transient conditions that create dynamic patterns of air temperature. We characterize them as cycles, drifts or ramps, step changes, stochastic or random. But these represent conditions that can occur in the field as well. Bottom right, these are other examples of temporal conditions that we, again, might experience locally or asymmetrically on our bodies. It could include varying radiant conditions from the facade as the sun moves in and out of a cloud, or again, the heated and cool chair, where we've seen one person can operate it differently during the day. So I think by organizing these experiences and these ideas into a matrix, what I'm proposing is that frameworks like this can be tools for organizing either research questions or maybe even design strategies. So the columns can relate to the ideas about spatial or temporal alesthesia that could be studied further in research. The rows might relate to how we both design and operate buildings to either recognize something that's going to be happening climatically or that we're intentionally designing and creating those variable conditions. So while I focus today on thermal qualities, I think it's really important that designers think about sensory space in terms of all four of the classic categories of indoor environmental quality, including lighting, olfactory, and acoustic sensory experiences. I know I showed this slide very early in the thermal comfort lecture. But when architects design, we're commonly thinking about space in terms of geometry and dimensions. How big, how small, how tall. But if I asked you, what is the shape of this space? You can't even see the dimensions, right? This is an example of space being defined by the senses, right? In this case, in light. And although you might be sitting with everybody in one room that is defined by walls, you can alternatively describe whether a person is inside or outside the boundaries of this light space. And returning to our focus on thermal space, what if we thought about the shape of space in terms of thermal experience? And I picked these images specifically to suggest or to remind that our perception of thermal space is not just about temperature. And as designers, we should be thinking about air movement and evaporative cooling and bodily cooling and connection to the outdoors and the effects of windows, and really thinking about all of the elements of the space that might affect our thermal experience. So how do we get architects to design for thermal experience? What if the answer isn't just the thermostat and tighter set points and more controls, but we think about more intentional thermal variability of spaces, a sort of what I like to call thermal landscaping, where we break down this false dichotomy of outdoors versus indoors. And we think instead about transition spaces. This is work done by the firm Atelier 10. Their local office in San Francisco has wonderful people who do quite a bit of this experiential design. You might think about these as unrolled visitor experiences diagrams, similar to what we were asking you to do in the design project, where they are purposely choreographing people's experience as they take different pathways through the built environment. And they did this on this project in Kuwait, where they were intentionally creating and diagramming these experiential zones along pathways that purposely varied from neutrality, that helped people go from the very bright and extremely hot extremes of outdoors to the air-conditioned and steady experiences of indoors, but having a variety of experiences along the way that were intentional. But I don't think we can or should entirely choreograph one sensory experience of space. I think it's really important that variability goes hand in hand with adaptive opportunity, where people can choose where they sit, where they're able to modify shades or diffusers, maybe even move furniture. Maybe open windows, turn on fans to get access to increased and variable air movement. And we're seeing a resurgence of fans, I think in large part to manufacturers finally creating really beautiful and contemporary models, because aesthetics is and should be important to increase the architectural acceptance of fans. So our research team at CBE is doing a lot of research on air movement. We believe it's an important and underutilized quality of the thermal environment. We think that fans can help us provide personally controlled and fast responding comfort at lower levels of energy consumption. But in addition to creating variety in the indoor spaces, weather permitting, I think we should also expand what I like to think of as the experiential perimeter zone in buildings, and not just think about we're inside or we're outside, but maybe we can be creating more functional outdoor spaces along the perimeter where there's more of a transition. And in doing so, I think all of these design strategies and technologies need to begin with a fundamental change in our attitude. We're valuing rather than fearing variability, and we're celebrating the sensory qualities of space. So this image here, which is going to close this part of the lecture, but hold on. This is from the cover of a wonderful book by Barbara Irwine that I encourage all of you to check out. So with that, I wanted to transition and tell you a little bit about a book project that I'm working on. But before I do, let me check the chat. Let me see, can you define temporal anesthesia again? Temporal anesthesia is about when our bodies experience a change over time. It's very often associated with transition spaces. So when we move from a cool to a warm space. So it's often considered a whole body experience, but it changes over time. Okay, well, if you have more questions, type them in. All right, so I've got a new project that I'm starting that I'm really excited about, and it's my first book. I've probably written 100 scientific journal papers, but I've never written a book, and I'm really excited to do it for the first time, and I'm really excited to be doing it with my dear friend and colleague Mark Decay from University of Tennessee. Some of you are familiar with his book, Sun, Wind, and Light. I hope you're familiar with it because we reference a lot of these sections in our readings. He also wrote a book that's more theoretical called Integral Sustainable Design. And Mark and I are both different, but we're kindred spirits in terms of this idea of experiential design. So he's an architect by training. I'm an engineer by training. He writes books. I do journal papers. He works more in isolation. I work more in collaboration. But we've always had this interest. So we took this project on, and I think that this is the week we're signing the book contract. So I'm really excited about that. We've been working with a publisher for a while, and so I'm really thrilled about celebrating the end of this semester with diving back into this project. So we've been dabbling with it, but we are about to get fully immersed. And I haven't talked to too many people about it. So this is kind of fun to be sharing this with you. So the working title of this book is The Feeling of Form, an Architecture of Sensory Variability. And I really see it as the intersection of building science and health science translated into architectural design strategies. Our audience is primarily design practitioners and students. It's not, we're looking at research evidence for how these different sensory experiences affect us psychologically, physiologically, cognitively. But most of the book is really based on design strategies for making these kinds of things happen. So this is the current table of contents of the book, where we'll start out with setting the stage with some theories about how these kinds of sensory experiences affect our bodies. Chapter 3, Making Sense of Sensescapes, is where we're going to be providing evidence. But the heart of the book is Chapter 4, which is designing these sensory schemas. So what do I mean by that? Well, first of all, even though this book is, I don't know, there's a bullet floating around on the bottom, you can ignore that. So this book is mostly about thermal, light, acoustics, olfactory environments. But instead of organizing them like that, we're actually going to be organizing the book on what we call these patterns of variability. So what is it that our bodies feel, and how do we organize things in terms of the different patterns of variability, contrasts, where you've got something that is really distinct between a hot versus a cold environment, where you're putting your foot in the cold water or you're walking abruptly from a hot to a cold space. So this is an example of the temporal alesthesia. But a lot of spaces actually create more gradients, right? So this is Georgia O'Keeffe's house, where there's this roofless, there's a trellis over this courtyard, so it doesn't really have a roof, it's open to the sky, but there's this real gradation depending on the density of the trellis and where the sun's coming in, where you can be in full sun, you can be in partial sun or shade, or you can be in complete shade. And it's a little bit like what you might be creating in your 140 projects as well, where maybe there's some places where the direct sun comes in, but you're making sure that's not on the artwork. And then there's other places where there's more diffuse light, and there's other places where you go into darker regions for the fine art. Another pattern is sequences. This is very much associated with people's movement and how we move from one place to another. The image here is the Indian Institute of Management in Bangalore, where there's these beautiful paths where people are intentionally walking from different variations of lightness and thermal experience. Rhythm is often connected to the natural cycles of climate, whether it's solar controlled or daylighting, whether it's the passing of time of day, passing of season. You're doing this in your project as well, where you're thinking about how your buildings perform in the morning, the afternoon, in the winter, in the summer. So even if you didn't give it the name rhythm, this is very much what you're thinking about. Stochastics is referring to randomness, but how do we connect some random ideas, some random patterns of nature, such as the Maple Valley, Washington Library, where they collect rainwater and then they have this visible cistern that fills up and it ebbs and flows as the rainwater is connected, and you get some connection to the rhythms of nature. And then narratives, it's a separate category where it's a little bit less related to the patterns of the physical elements of the environment, and it's more about a narration, such as this example of the Turtle Creek house in Dallas done by Antoine Predock, where there's a really strong narrative about these different levels and connection to ground or to sky. Oh, let's see. All right. I noticed another typo. I was doing a lot of this morning, adding the book stuff. Like I said, I haven't talked about this to too many people, so I was throwing this together. So I apologize for random bullets and spelling errors. So thank you, Jacqueline, for pointing that out to me. All right, so the other really fun thing, that's how we're organizing that chapter, but then each of the schemas, we're going to have about 40 or 50 schemas, and they all have these various poetic names. So even though they're connected to light and thermal and acoustics, we want names that really reflect the experience, not just the physical element. So the entry sequence is about how we might move from outdoors to inside. Engage the Rain is about this wonderful idea of having the peripheral porches and buildings being protected from the rain, but being open. So often in warm climates, you want to be inside and you want to be able to smell the rain and hear the rain and see the rain. Circadian spaces is very much connected to rhythms, where the quality of light in the morning and the dawn and from moving to dusk really affects our circadian health. Haptic connection is about touch. This is a wonderful example where there's these warmed benches that you can sit on, and that's very much an example of spatial alesthesia. Courtyards are wonderful examples of multisensory experiences where you can connect to water and variation of light and sun and shade patterns. And Zephyr Spectrum is an example of how you use air movement to create both variations in calm and breezy spaces. So these are the names. What is a schema? A schema is a way of talking about how we organize space in order to create these experiences. So the heart of the book is going to be these 40 to 50 schemas, which are each 2 to 4 page spreads. Sorry, that must have been on automatic transition. So each of these spreads are going to have a name, such as what I gave you. Examples of, it's going to have images of precedent. There'll be a narrative explanation of how we experience these sensory notions. We're going to have design guidelines, how do you create them, and then supporting evidence about what do we know about how these experiences might affect us. And then I'll just end with this last slide, which is just an example of one of these pages on Zephyr Spectrum about how we can create breezy and calm conditions. And so we'll have 40 to 50 of these kinds of patterns. And with that, I am done. I will stay on for any questions people might have. And I hope you enjoyed the lecture. I hope you enjoy the book when it eventually comes out. And thank you. That's it.
Thank you.
Thank you. I love seeing all your thank you comments because it's so weird talking to a screen.
Gail, I don't know if you noticed, but I think there was one question before many of the thank yous.
Oh, thank you. I'll scroll up. Oh, I do see it. Michelle, I don't know if you're still on the call. I see, do you know of companies who are trying to incorporate transitional functional space or natural airflow into their office designs? Well, a ton of people are doing natural ventilation, and a lot of them are doing it as mixed mode. So you can have both operable windows and mechanical cooling. Google is actually doing some really interesting work where they're playing around with these ideas of variability and experiential delight. And so they've been doing a lot of work on that. Atelier 10 is a consulting firm, and any of their projects, they've been trying to integrate this as well. Gensler did a whole project. Hey, that was my dog chasing squirrels. Gensler is actually doing a whole project on an experiential index, which is a little bit different than the experiential design we're talking about, but they do a lot of interior work where they're trying to get into this as well. So I hope if you're still on the call, Michelle, and heard that.
Yeah, thank you.
You're welcome.
Tell Toby we said hello.
Yeah. Chasing squirrels. All right, I'm closing it down. I enjoyed sharing that with you, and I will see you guys on Wednesday. Bye.